Okay, let's go to two-dimensionalizing model and summarize. As I told you, this one, contrary to the one dimension, has a phase transition, and there is an analytic expression for Tc, the critical temperature, solved by Onsager, 1946. Well, the exact solution is given in chapter 12 in your book. And as I told you, Huang's book also has a 20-page solution. Here we have a two-dimensional spin lattice. So there's something like this, going for n spins. So it just goes. Okay. Now to label spins, you need two subscripts now. This is 1, 1, 1, 2, 1, 3, etc. 2, 2, 1, 2, 2, 2, 3. So it is a two-dimensional lattice. You can label these spins, and you can write the Hamiltonian as follows. Again, J taken to be positive is going to correspond to ferromagnetism. We have two labels, Ij, for each spin. Sigma I plus 1j and sigma I j plus 1 sigma I j. This is the interaction term in the symmetrical form, and this is the external field term interacting with the spins. You can introduce a shorthand notation for this and write it as J from 1 to n E mu j plus 1 plus E mu j, shorthand notation, where mu j, mu k is defined as minus is that term, and E mu j includes the interaction again. There must be j here too, I think. There must be a j here, isn't it? Well, mu j is defined as a set of spins in a particular column. So this is defined as sigma 1j, sigma nj. So this is spins in the jth column, isn't it? One, three, and three. This is a column, third column, isn't it? Okay. Now we can define a transfer matrix as we did for the one-dimensional case, for this two-dimensional Ising model. Let's call it P this time, so that mu j, P, mu k, columns, two columns, is e to the minus beta, e, mu j, mu k, plus e mu j. So it is just a notation. I think if you are interested, you can go to chapter 12 and see the whole calculation. So this is 2n by 2n matrix. It's a large matrix. So you are going to look at the partition function, which is going to be given by trace of transfer matrix to the power n, like the one-dimensional case, and we have to concentrate on the largest eigenvalue. Again, this problem is 20 pages in Huang. You can read that. Here is the summary of the solution. So let's look at the solution in this case. Energy per spin comes out to be as a function of temperature is minus 2j tangent hyperbolic 2 beta j plus k over 2 pi dk over dk d beta integral from 0 to pi d phi sine squared phi divided by delta 1 plus delta, where this k is 2 over cosine hyperbolic 2 beta j cotangent hyperbolic 2 beta j. Okay? You have to do some work. Delta is 1 minus k squared times sine squared phi. In this case, there is a phase transition. Here is the expression. magnetization comes out to be well, M is 1 minus sinus hyperbolic 2 beta j to the power minus 4 everything to the power 1/8 0 otherwise. This is for T smaller than Tc, critical temperature. This is for T greater than Tc. So there is no magnetization above a critical temperature. There is magnetization below that critical temperature. So that means we have magnetization, we have spontaneous magnetization, even in the case H equals 0, applied magnetic field equal to 0. That's why we call it spontaneous. So as far as physics is concerned, the spin-spin interaction is responsible for this. It is such a strong interaction that it locks the spins in the same direction because it lowers the energy when J equals positive. You can determine the Tc, the critical temperature. The condition for this is 2 tangent squared to beta j is equal to 1. That gives you a critical temperature, kBTc, 1 over the beta, approximately as equal to 2.269181.5 J. So the critical temperature is proportional to J, the interaction parameter. That is the proof that a critical temperature exists. So you can write the other thermodynamic properties of this two-dimensional spin lattice. For example, the heat capacity, specific heat capacity per spin can be written as C of T over Kb as 2 over pi 2J kBTc is minus 1 plus pi over 4. This diverges logarithmically when temperature comes close to Tc, the critical temperature. Critical exponents can be found. I gave you an example how to find this. There is a divergence. Beta comes out to be 1 over 8. Gamma comes out to be 7 over 4. Delta comes out to be 15. So it is completely analytically solvable. If you write the heat capacity plot it. For this two-dimensional case. Both has energy units, interaction parameter, and kBT, thermal energy, and C, exact solution is something like this. And there are approximations, well-known approximations. You can read the book. You have to. For example, mean field gives you something like this. This is exact Von-Sager solution. Okay. So in short, this is really a very short introduction to the model, just to make you interested enough to read, study in detail, if you like, the exact solution. There is a well-defined second-order phase transition, and heat capacity has this interesting form. Now I want to tell you a little bit about the mean field approach. Do you know what mean field approach is? I told you this a couple of times in my lectures. Do you know what mean field is? Have you seen this before? Anywhere? From your faces, I see. Even if you heard it, you don't know what the hell is going on. Okay, I think it is a simplified approach. Let me introduce the concept at least, and show how you can solve it in that approximation. Instead of the exact solution, let's go to approximations. Mean field approach is interesting, and it's very common in physics of many particle physics. Mean field approximation. The aim here is to focus on a single spin. Okay? Instead of considering n spins, you consider only one single spin and kind of think that that single spin is under the effect of all the other spins around interacting with it. So the other spins are creating an effective mean field at the position of that spin. So you can write the interaction of that spin with the mean field. Okay? Here's the approximation. Well, let's write the Hamiltonian, Ising Hamiltonian, as minus j. Well, interaction between spins, spin-spin interaction that aligns the spins in the same direction, minus j, the field term. This is the applied field term. Okay. Now, focus on spin I. So it is a single spin in some sense, single spin approximation. Sometimes it's called one body approximation. Okay? So let's find terms depending on spin sigma I. So let's write this Hamiltonian as J sigma I sum over J, which is nearest neighbors of I, okay, whatever is the geometry, consider only nearest neighbors, sigma J minus H sigma I. So let's write this approximately as minus J sigma I sum over J nearest neighbors, average spin, average field, mean field, okay, minus H sigma I, and that turns into something like this. Minus H plus J Q M times sigma I. Q is the coordination number of nearest neighbors. But if you have a square lattice, it is 4, isn't it? Any spin has 4 nearest neighbors around it. That's coordination number 4 for square lattice. In a one-dimensional case, it is 2, isn't it? 1 on the left, 1 on the right. So M is the average magnetic dipole moment or magnetization, this average thing. We can also write this as sigma I from plus minus 1 sigma I e to the beta JQM plus H sigma I divided average sigma I, again sigma I e to the minus beta JQM plus H sigma I. Or this is nothing but tangent hyperbolic beta H plus JQM. This is Curie-Weiss mean field equation. Well, there is M on both sides, So we can try to solve this graphically, isn't it? For h equals 0, we are always looking for external field equals 0 solution because that will tell us whether there is spontaneous magnetization or not, isn't it? So it must be a self-consistent solution because both sides have m. A graphical approach tells you the following. Well, m is just a line going through the origin. Tangent hyperbolic is something like this. Well, it goes like this, isn't it? That is tangent hyperbolic beta jqm. I have drawn this for t greater than tc. So there's no magnetization in this case. They cross each other and zero magnetic field, zero magnetization. This is m. Those are the both sides of this equation. Okay? There's no magnetization if T is greater than the critical temperature. But if T is smaller than the critical temperature, let's see what happens. Well, again, there is M. And this time, the tangent hyperbolic becomes something like this. So you have two solutions. M minus M plus. This is tangent hyperbolic term. So now we have magnetization for T smaller than Tc, or beta jq smaller than 1, and critical point is at kbtc equals j times q. So you have a phase transition in this case. So even this mean field approach is giving you a feeling for the appearance of a magnetization in the absence of applied magnetic field. That means spontaneous magnetization. So if you plot M as a function of temperature, you see that you have something like this, -1 +1. This is Tc. Proportional to C times Q. Okay, I think this is also an interesting approach, and you can see this in the case of a solid, for example, when you study the electron physics, to concentrate on what the electrons are doing. You have lots of electrons around. So you concentrate on one electron approximation and see that it is moving in the field of all the other ions and electrons. So you introduce an effective field, which is represented by a crystal potential. Okay? That's also one electron approximation, one body approximation, a mean field approximation. Here we did the same thing. We concentrated on one spin, separated that from the rest, and wrote the Hamiltonian as a single spin interacting with all the others through a mean field created by all the others in the problem. Do you have any questions with this? Can you get the mean field critical exponents? Can I ask you a question about this? You are not sure. Can I ask you a question about this? Okay. Now in the last lecture, I will tell you about Landau approach for second order phase transitions, like the ferromagnetism. And Landau approach is a mean field approach, mean field-like approach, but he concentrates on the Helmholtz free energy and turns it into Landau free energy, okay, near the critical point. If we do that, I think we cover in a summary form the whole approaches, at least introductory approaches to phase transitions. Just to summarize, in this interactions part, we have seen weak interactions causing a restructured equation of state, van der Waals equation, this interaction including repulsion and attraction between particles. In this case, we have started with a model Hamiltonian, which is Ising Hamiltonian, which was very simple, just collection of numbers, but corresponding to spin interaction. And in one dimension, we have seen nothing, no phase transition, no ferromagnetism, but in two dimensions, there was explicit analytic solution for the critical temperature, and there was a phase transition. And we have introduced this concept of mean field. Now we are ready to do the Landau approximation.